Okay, so greetings, welcome to week 10, and today we'll be doing two questions, one on Bode plot and one on Nyquist. So uh, let's get started. The first question is giving us a negative feedback closed loop system whose open loop transfer function is given here. We have to first find the closed loop transfer function. Then using the closed loop transfer function, we have to find the static position error constant. Uh, then we have to draw the Bode plot of the given system and highlight these attributes. We have to highlight the DC gain, slope of low and high frequency asymptotes, the magnitude plot, and the corner frequencies in radian per second. So, let's get started. The transfer function given to us is g of s, which is s plus 1 over s square plus 12s plus 20. So, this is closed loop transfer function. So, let us write this as g of s, h of s. Okay, apologies, this is open loop transfer function. So the closed loop transfer function would be g of s h of s over 1 plus g of s h of s. So the closed loop transfer function would become s plus 1 in the numerator and s square plus 13s plus 21. So what is static position error constant? Static position error constant is given by limit tending to 0 g of s h of s. So as s tends to 0, the numerator becomes 1 and denominator becomes 20. This is first portion and this is second part what we have asked in the question. Closed transfer function and static position error constant. So to draw the Bode plot, let us take the open loop transfer function and factorize the transfer function. We have s plus 2 and s plus n as the factors. So let us write it in the familiar form where the factors can be utilized. So I'm taking 20 common here so that I can write s over 2 plus 1. So 2 comes common from here and s over 10 plus 1. So, so we can utilize this when we are drawing the Bode plot of individual components, after which we can draw the combined Bode plot. So to calculate DC gain, we have to take limit omega tending to 0, 20 log 10, sorry, 20 log base 10, magnitude of this transfer function where s has been put as j omega. So it will be j omega plus 1 in the numerator and j omega square plus, so when you apply the limit, it would be 20 log base 10 1 over 20. So this comes out to be minus 26 decibels. So now let us draw the phase plot and magnitude plot. So okay, so let's take 20, 0, minus 20, minus 40, minus 60. And we'll take 0.1 here, 1, 10. So in the x-axis, we are plotting magnitude in decibels, and on the y-axis, we are plotting log of frequency. So frequency we are plotting in logarithmic scale, 10 and 100 and 1000. So we had several components here. We have 1, 2, and 3, and we have a multiplier of 20. So let's write down various components and draw the Bode plots of each one of it. So I'll be using different colors here for convenience. We just draw some horizontal lines. So we have just calculated this DC gain, which is minus 26 decibels, which will come somewhere here. So let's draw a horizontal line here. 126 decibels. So the first one we have is S plus 1. So since this is in the numerator, so the slope of it would be positive. Since it is first order, slope would be plus 20 dB per decade. So and it will, yeah. So we start from 0 to 1, and at 1 this would go to, so this has slope of 20 dB per decade. So this component corresponds to S plus 1. This one corresponds to 1 over 20, which is the DC gain. So the next one would be the component of 1 over S by 10 plus 1. Right, so we will be focusing now on this part. Hmm. So here we have 10 in the denominator, so that means our frequency would be 10. So S over, so let's draw a line at 10. It will be 0 till this frequency, and at the crossover frequency of 10, right, the second asymptote would come, which will have slope of minus 20 dB per decade. So this component is 1 over S over 10 plus. Now the next component is this 1 over S plus S over 2 plus 1. So here somewhere at 2 will continue to hold 0 till this point, and then we'll have slope of minus 20 dB per decade. Alright, so we have drawn uh, all the components, the DC component, the two other components. So if we were to draw the final Bode plot, which combines all these, it would start at the DC gain, continue till here, and then the component of S plus 1 would start dominating, hence it will go up, and then it will, the component of 1 over s by 2 plus 1 would compensate for the plus 20 dB decade slope and minus 20 dB per decade slope till this point, and then uh, it would start following the 20 dB per decade slope. So something of this sort would be the final Bode plot. So at lower frequencies up to omega equals to 10, the DC gain would be the magnitude. If you provide us, so for example, if you provide a sinusoidal input to the system with frequency in this particular range, this will be the gain, and in this range, this would be the gain of the system. That means if you provide a unit magnitude of sine wave, you will see the magnitude drop 1 by 20 at the initial point, and as the frequency increases, this is how the magnitude would behave for a frequency response with unity input or unity magnitude. So similarly, now let us draw the phase plot. So here we are plotting the phase and the frequency omega. So let's draw the three lines. This is for 0 degree, 90 degree, and minus 90 degree, and intermediate points of plus 45 and minus 45 degrees. Let's draw vertical lines at crossover frequencies. So this was 1, this is 2, and yeah, that's, then this is 10. So let's draw for the s plus 1 component. At the crossover frequency, it will have value 45. So we'll start from 0 and follow this. So this one is s plus. Now let's draw the next one, uh, which crosses at 2. So this will be the point on it. This orange component would be 1 over s plus 1 over s, sorry, 1 over s by 2 plus 1. And let's draw the third one, which would cross the 45 degree here, something like this. So if we combine the plots, it will be 0 till this point. and somewhere like this it would come up. So of course the DC component of 1 over 20 will have 0 as phase. This is the final phase plot. The corner frequencies here were at omega equals to 1, 2 and 10 radian per second. At the or these the components, and the angle g of j omega is 0 degree plus tan inverse omega minus tan inverse 0.1 omega minus tan inverse 0.5 omega. So the 0 is because of the DC component, tan inverse omega because of the numerator term which has corner frequency of 1, and then the negative signed terms are corresponding to the poles, or the denominator portion which is coming, uh, which is corresponding to the corner frequency of 10 and corner frequency of 2 with 0.1 omega term and 0.5 omega term respectively. So you can, if you sample all these plots, if you sample the equation for this angle, you can figure out what all points will be on the Bode plot. So that is all about the Bode plot. Next, we would be drawing the Nyquist plot for these two transfer functions. So let's start with the first one. So I'll just substitute j omega instead of s, and let's multiply and divide by 4 minus j omega so that we do not have the j term in the denominator. Now that we have this, let's take the magnitude. So if we take the magnitude of j omega, this will be this. And if we write the angle term, since we have this s plus 4 in the denominator, it will be omega by 4. So let's see with respect to omega. where is the real part of omega. So real part of g of j omega, imaginary part of g of j omega, and the angle of g of j omega. So when omega tends to 0, the real part would be 4 over 16, that is 1 over 4. So 0.25. As again, as omega tends to 0, the imaginary part would be 0. And when omega is 0, tan inverse 0 is 0. When omega tends to infinity, so the first portion, the real part would become 0. It has omega square in the denominator. In the imaginary part, we have, if omega tends to infinity, it would be infinity by infinity. So we can use L'Hospital's rule, and then we'll be left with j in the numerator and 2 omega in the denominator. So since omega is in the denominator and it's tending to 0, uh, sorry, it's tending to infinity, we would have 0. And so the angle term when omega tends to 0, so sorry, when omega tends to infinity, tan inverse infinity would be 90 degrees. And since we have a minus sign in front of this, it will be minus 90. So third thing, when omega is equal to 4, uh, so that is where 1 over s plus 4, s equals to, sorry, yeah, since the corner frequency here would be 4, right, if we write it in this form, 1 over 4 in bracket, s over 4 is 1. So, and we compare this with some, so now would be 1 by 4 and omega would be 4. So at this corner frequency of 4, the real part would be 4 over 32, that is 1 by 8, so it would be 0.125. And if we put 4 here, we would be left with omega by, so 4 over 16 plus 16 again. So this will be minus of 0.125. And if we plug in the 4, it would be tan inverse 1, which is 45 degrees with the minus sign. So now that we have this, we can draw the Nyquist plot, imaginary axis and real axis. So we know 2 points, 0 on the real axis when omega tends to infinity. So this point will be there, and this point will be there, which is 0.25. This will be when omega tends to 0. So uh, in either case, this we have 0, 0 in the imaginary part. So we can plot this one point, which is this, and we can plot this one point, which is this one. So we can draw a semicircle here, coming like this. So we can draw this semicircle here. So why is it in the negative side? Because the angle terms are negative and the radius here is 0.125. So when you look at the corner frequency of 4, you can see 0.125 and my j, sorry, negative j 0.125. So this point would be on the curve. So as frequency tends from 0 to infinity, this would be the direction of travel. So the second part is g of s plus 2 and s plus 10. So let's multiply this with 10 minus j omega divided by 10 minus j omega. So this would turn out to be this quantity. If you write the real part of j omega, this would become 20 plus omega square by 100 plus omega square. And the imaginary part would become, so again if we take a look at omega, real part of g of j omega, we can write these things and let's also write angle here. This would be 8 omega over 20 plus omega square. And, so that is the imaginary part over the real part and tan inverse. Alright. So when omega tends to 0, the real part would be here we have 20 over 100, that would be 0.2. When omega tends to 0, the imaginary part would tend to would be 0. If we substitute 0 in the numerator, it will become 0. And the angle term, this will also be tan inverse of 0. So 0 degrees. When this tends to infinity, we have so same so we have a quadratic polynomial in the numerator and quadratic polynomial in the denominator, and the coefficient happens to be the same. So if we take the limit of omega tending to infinity, this would be infinity by infinity, and if we solve this limit, it would come out to be 1. Similarly, if we put infinity here, it would be infinity by infinity, and after applying uh, an hospital, we'll end up getting 1 omega term in the denominator and constant in the numerator. So when omega tends to infinity, this would be 0. So same story would apply to the limit in the angle term, and we would get 0 degree as the angle. So in the similar way, if we draw imaginary axis and real axis, let's plot this point 0.2 comma 0 and 1 comma 0. So if we draw this, so if we take the angle at the crossover point, okay, hold it, just 1 second. So uh, all right, so the difference between this would be 1 minus 0.2, that is zero point 0.8, which is the diameter. So radius here would be 0.4. And if we draw this and want to find out this angle, say Pm, this would be sine inverse of 0.4, which is this side, over 0.2 plus 0.4, that is 0.6. This would come out to be 41.8 degrees. And this is where omega tends to 0, and this is where omega tends to infinity. So this is how the Nyquist plot would look for the given transfer function. So any points to discuss?
No, boss, it's pretty clear.
Okay, looks like we have some 10-15 minutes if you are willing to spend. Would you like to discuss something else?
Yeah, sure. No problem.
Okay, so today we will just, last time we checked out some discussion on controllability, sorry, observability. So this time let's truly try to understand what controllability means. So with controllability, we are trying to ask ourselves a question: can the states of the system be uh, modified from any initial condition to any final condition infinite amount of time. That's control input. Which means if you are say at this point, it's not. And if you want to be here, say xn, then you take some moves, then you find a series of control inputs, say u0, u1, u2, and so on, say un minus 1, so that you reach the final desired state as xn. Okay, so this is the question we ask with controllability. In observability, we ask, can we uniquely determine the initial conditions, uh, initial state, given the series of measurements and series of control input? Here we are asking, can I go from any state, arbitrary state x naught to any arbitrary state xn in finite inputs? So we can have multiple inputs. So the question here is of existence of such series of input. Whereas the question we asked in observability, a subtle difference is that that question is of uniqueness. So with that subtle difference, let's write the discrete time state space equation xk plus 1 is equals to axk plus buk. So here only we are worried about xk's. So if I write say x1 is equal to ax1 plus sorry ax0 plus bu0, what I can write it x1 minus ax0 is equals to bu0. So let's keep this equation in mind. Now let's write x2 is equal to ax1 plus bu1. So if I substitute x1 here, then let's see a into this would be x2. So if I do x2 minus say a square x0 is equals to a into b u0 plus bu1. So let us call this as x bar 1. Let's call this as x bar 2. Alright, so what we are trying to do is, uh, given the states and an initial state, with that assumption that we know the state and the initial state, we are trying to find out series of inputs. So far we have u0 and u1. So if I were to write x3, let's try one more time. So it would be ax2 plus bu2. So if I were to substitute x2 here, uh, this x3 would be written as a in bracket a square x naught plus abu naught plus bu1 whole in bracket plus bu2 of course. So we are kind of looking at a pattern. If I write x3 bar as x3 minus a cube x naught is equals to du2. So let's see if I keep on writing this x3, x4, x5 up to xn, uh, then I can write x bar n as xn minus a power, so a power n x naught is equals to a power n n minus 1 bu naught plus a power n minus 2 bu1 and a power n minus 3 bu2 and so on. We'll have a into b u, so n minus 2 plus bu n minus 1. So since we are going up to n, control inputs would be up to n minus 1. So if we write this in a matrix form, a power n minus 1 into b, this will be one column, a into a power n minus 2 b, and so on to ab, and finally b. So this can be one column or a matrix which is getting stacked one after the other into the u vector u naught, u1, u2, so on up to un minus 1. So let's denote this entire thing as capital U. Let's denote this entire matrix as C, and this x bar n we already know. So this again uh, we can write as C into U is equals to x bar n. So this is similar of the form Ax equals to B, what we have been looking at in linear algebra. So if C is full rank, that means C would be invertible. Okay, since C is invertible, this means the equation has a solution, and if the equation has solution, there exists at least one set of inputs u, which can take you from, can go from which can take your states from x naught to xn. All right. So that is the discussion about controllability matrix. So if your system is fully controllable, that means you can modify all of your states by giving appropriate control inputs. And if it is observable, completely observable, that means you can also observe the states of the system. So, do you have any questions here?
No problem.
All right. So, I think. Thank you for joining. I will stop recording now.
Thank you.